Okay. Are you guys able to see this? Okay. So guys, today we'll be talking about work power energy. So it is actually a like easier chapter than compared to NLM. Initially, when you're learning NLM as a 11th standard student, you will see that you might find it a bit difficult because you will learn about constraint equation and then the other different varieties of problems like wedge constraint and then string constraint and then pulleys and relative motion is also a little bit there, and then pseudo force and all. They get a bit confusing, but if you're able to really understand NLM properly, then WPE is just work per energy is just cakewalk, honestly. So well, it is also very important because 11th chapters, be it NLM, be it kinematics, or be it work power energy, these three chapters really help you in 12th also. Okay, so whatever energies, whatever derivations you're going to be seeing in 12th, the base foundation comes from mechanics. That is from the 11th topics. Okay, so what is work? You see, okay. So work is basically, if I just write in layman language, it is the dot product of force and displacement integral. Okay, this is work. Okay, so this is, okay, I'll write that like this. So work is force dot displacement. Just remember this. Okay, so any foundation or like any derivation for any of the energy equations, be it kinetic energy, be it potential energy, or be it any other form of energy, it comes from this formula only in mechanics. Okay, so I'll just show you one more thing. So let us have a small interaction about work. So work is basically, like I said, it is integral f dot ds, right? F dot ds. So this F dot ds is so important. This work term of work is so important that you will study it in even after 11th, after 12th also. I'm a BTech. I'm studying BTech right now. Even we have to understand the concept of work here. We have a topic called thermodynamics. We have a whole course about it. So be it whatever branch you are, you will have this course of thermodynamics, and in that, one of the most important term that comes is work. There we define work as uh, integral pressure into volume. Okay, this formula you will also learn in our 11th topic of thermodynamics, be it physics or be it chemistry. You will learn it in both. Okay, so this is foundational, this is fundamental. So this is for in 11th the mechanics topics that you will be learning, and this comes under thermodynamics. Okay, work equal to integral fpv, f dot dv. So you'll be having different graphs. In thermodynamics, we'll learn it better. Like for a graph plotted between P and V, we call it an isotherm, this graph. So if we have any arbitrary graph like this, so work represents the area under the curve. Okay. So this you see, this is the area under the curve. This is called work. Okay. So for work there is different conventions. Coming to thermodynamics, you will have a convention there, negative or positive, but in mechanics, that is work per energy, here the convention is basically this. If you have a block like this, a force, let's say it is acting at this angle from the horizontal, that is theta f, and it is displaced about, let's say, s displacement, then work is f dot s vector, and this is basically fs cos theta. Okay, let's write it neatly. Fs cos theta. Okay, so what is this fs cos theta? So basically it is f cos theta times s displacement vector, right? So if you see here, this block has this block has two components. One is f cos theta and the other is f sin theta. So basically, now that you learned NLM, you might understand that if you consider only this block as the system, then if you look at the blocks FBD, if you look at the blocks FBD, the external forces that are acting is on the block. The forces acting on the block are normal force, gravitational force, and then this external force F. Okay, so I have basically divided this F force in components here. Okay, so this what you see, this component of force F cos theta, this is what is causing the displacement. Okay, so if I have a displacement in this direction, then F sine theta, let's say it y. So F sine theta is the force that is causing the displacement or the work in the vertical, in the y axis. Okay, and F cos theta is the force component of force that is causing it work in the x direction. All right. So okay, I hope till now it is understood. Any doubts you can ask me right now. Okay. Okay. So there is a question. I want you all to solve this. Okay. No doubts. Okay. All right. After the end of this session, we'll have a small interaction. Okay, for like 5 or 10 minutes regarding your preparation. Okay. So solve this question. I'll give you 2 minutes time. It shouldn't take much.
Sir, approximately how long will the class be taking?
It will be for 1 hour. It will be a short session. If needed, I'll also take a separate session tomorrow or day after tomorrow for only for problem practice. Okay, so this is basically a brush up or a revision.
Okay, sir.
Okay, I'll wait 1 more minute. I want you all to solve this question and tell me the answer. Okay, so I'll start it now. So it is mentioned that assume a body is displaced from this position vector to this position vector, that is from A to B, under a constant force. This is the constant force. Okay. Now he's asking us to calculate the total work done. So this we are talking in terms of 3D plane. Well, nonetheless, we'll go with the basic definition. That is, force is F dot ds, or let's say force is F dot displacement vector. So this formula that you see here, this we use for variable forces or variable displacement. But in this question, the force, it is mentioned that it is a constant force, and the displacement doesn't seem to be variable. So we'll just directly use this formula. So now the force F dot displacement is, it went from RB final vector from initial vector. Okay. So it is 2 I cap plus 3 j cap minus k cap dot uh, 6 minus 2 I cap, and then minus 4 minus 4 j cap, and then it is 2, okay, sorry, 2 plus 6 k cap. Okay, so if we take the dot product, this will be 4, that is 8, and this will be minus 24, and this will be minus 8. So it is minus 20, 24 joules. All right, it is minus 24 joules. The answer. Okay. So, like I said, okay. So I missed one topic here. So the thing is, uh, like I said, in thermodynamics, you'll see the reason I'm stressing about thermodynamics is because that is where you'll again get this term work again. So basically, in thermodynamics, you'll see that work has a convention. Like I said, it has a negative work, positive work. So it all depends on how whether it's expansion or compression of the system. But here in mechanics, the change of work that we see is, let me just if we have a body, like I said, in this we saw that the force is acting in this direction, in this f f at an angle of theta from the horizontal direction, right? So here, if you see in this example, if we take a force F acting at an angle, let's say some 120 degree, and the displacement is this way, F. The displacement is this way, and force is the component of force. Let's say, wait, I'll just draw it properly. F sine theta, and this is a displacement here. Okay, sine theta, and this is F cos theta, right? Okay, so if I ask you the work done here, only this F cos theta component is doing work, and as F cos theta is opposite to displacement vector, then the work done is negative. Okay, you can just go with the formula also. F is equals to F cos theta S bar, and there will be a negative sign here. Okay, so this is what the negative work uh, tends to. Okay, so now talking about the variable force, you can read all this, but basically variable force, only what we generally use is this formula: force is integral F dot ds vector. All right, so this is the basic funda we use, and nonetheless, like I said, work is area under the curve for force into displacement. Let's say we have an arbitrary graph, the area under curve that you see here, this is work. Okay, and let me tell you, there are some good level questions that can only be solved if you look in terms of graph. Okay, if you draw the graph, then only you will be able to solve, and I have seen some of these questions during my preparation. Okay, uh, when time permits, I'll show you those questions as well. Okay, so solve this question. I'll give you 1 minute of time, 2 minutes you take. Try to solve this question. Okay, it's a JEE main previous year question. Yes, Daksha, yes, it is 21 joules. Very good. So I'll start. So like I said, the formula is F is equals to integral F dot ds, right? So these are actually all basic level questions, just to brush up your concepts. Uh, I'll take another problem practice session. In that, I'll bring some good level of questions for JEE mains. Okay, so let's solve this. So 10 plus dx from x equal to 0 to 2. So it is 10x plus, yes, okay. Okay, so now we'll talk about conservative and non-conservative forces. So conservative, non-conservative forces basically means that you can read all this, but in layman language, let me tell you, conservative forces are those forces that basically they do not depend upon the path. Okay. So for example, the best example that we generally take is the work done by gravitational force, or what we call as potential energy. So if for example, if this pen is here and I have to bring it here, so I can directly bring it this way, or I can just do any sort of path and bring it here directly. So this won't matter much, because as gravity is a conservative force, the work done to bring this object from here to here is equal to work done from bringing this object to here and like this. Okay, so it the same amount of work it took to come. Okay, so this conservative and non-conservative forces, this basic idea will also come in thermodynamics again, wherein you'll see a path dependent function and a state function. Okay, so you'll learn it in chemistry, I think, but nonetheless we'll cover it when we are learning thermodynamics here. So non-conservative forces are those forces where path matters. Okay, so it is just basically you can read all this. So now we talk about power. So basically, power is the rate of change of work done. So basically, power you can write it as this way. Uh, uh, so if the force is constant here, we can write it as ts by dt. This is nothing but force into velocity. All right. So in more better terms, I can write it as force dot displacement. Okay, this is what power is. So power again, you will learn it. Well, coming to 11th and 12th, there is not much of a use of power. There are certain questions wherein you may find this term power, but this is the basic formula. It is the rate of change of energy or rate of change of work by time. Okay, so rate means change with respect to time. Okay, or else this is another formula that you are going to be using. Okay, f dot v. So try to solve this question. This is a good level question. Try to solve it. I'll give you 2 minutes. Okay. Okay, so I'll be starting it. So basically, it is given that a particle of mass m is moving in a circular path of constant radius r, such that its centripetal acceleration is varying with time t as this. K is a constant, okay? The power he asked here. Power delivered to the particle by the force acting on it. So we know that AC is the centripetal acceleration is v square by r, and this you equate it with this, and then V you will get it kRt, right? If you look at the path here of the body, let me just draw a better circle. There is a shape here. Okay, so if you see it here, uh, okay. If you see it here, uh, this is centripetal acceleration. This is tangential acceleration. So the velocity, you can see that velocity is varying with time, right? So this is the tangential velocity that is varying. So basically, uh, there is a force that is acting here, that is tangential force F is equals to m at, and so dv by dt, okay, m k r you'll take, because r is given as a constant radius. So force you got, now velocity is there, F dot v is equals to m k square r square t. So this is the power, right? According to the formula, this is the power. Okay. I hope you got it. Okay, so now moving on to the next concept, work done against friction. Well, this is not that much, but just remember that work done by friction is either zero or negative, but it can never be positive. Okay. So if when we come to some questions related to conservation of momentum, you'll also see that work done by friction does not depend on the frame. Okay. So let me tell you one important concept here. This usually a lot of people don't tell you. This is a good advanced level concept. I'll tell you right now. Add page. Okay. Yeah. So let me tell you, kinetic energy. Oh, sorry. That you write as half mv square. You can see that it has a mass term and a velocity term. So because of this velocity term, kinetic energy is frame dependent. Just remember this. Okay. Frame dependent. Dependent. Okay. Frame dependent. But if you look at friction, work done by friction force, work done by friction force, uh, let's say a body is here and it is moving this way, and there is friction acting here. So there is displacement here. So let me tell you that uh, the work done by friction, like I said, it is either zero or negative, but not positive. And the reason behind that is friction always acts opposing the relative motion. All right. So if here the relative motion is this way, motion is defined as the movement due to velocity. All right. So for friction will always act opposite to velocity. So friction is, as it is acting opposite to velocity, as it is acting opposite to the actual motion of the body, the work done by it is negative. And work done by friction is actually frame independent. And there is a reason for that. You see, work done by friction uh, is converted into heat energy. generally it is converted into heat energy. There could be other forms of energy as well, like sound and other type of energy, but generally it is converted, majority of it is converted into heat energy only. Even in industrial side also, be it any kind of machine, be it any kind of engine or any kind of piston, the work done by friction is generally converted into the form of heat, and it is released into the surroundings from the system. Okay, when you learn thermodynamics, you learn it a lot. Okay, we have a course here in bits, so that's why I'm like, it is very important. Okay, so and why is heat not frame independent? Well, heat is just heat. It is not dependent on frame. It doesn't have a fixed formula. It does not have any term of this uh, velocity or acceleration like that. If it had, then it is frame dependent, but heat is just heat. If you take it out of a bottle, or if you take it out of a piston, it is just heat. It just flows from one system to another system. So free heat is frame independent, and work done by friction is converted into heat. That's why work done by friction is frame independent. Okay, this is very important. I don't think a question was asked regarding this in JEE Means, but if they ask, then it is a very good concept, nice way to trap a lot of students. Okay, so just remember that kinetic energy is frame dependent, whereas friction is frame independent. And when we solve questions related to momentum conservation in center of mass chapter, there you will see we'll see good questions regarding this concept. Okay, so now coming to the next topic. Wait. So it is mentioned here that we know that frictional force always acts opposite to the direction of motion. It is written here. And hence direction of displacement. Therefore, the work done by friction is always negative side. Further, the work done by frictional force is invariable, lost in the form of heat and sound energy. See, like I said, it is mentioned here. Thus, it is a non-conservative force. Yes. It is path dependent. Okay, so path matters when we are calculating the force, like friction, the work done by friction. Okay, so basically you can just write it here. F dot ds, it is converted to heat. Okay, heat. You can put a negative sign, but it doesn't matter. If you're solving this equation, you will automatically get a negative sign, but we generally put it on our behalf. Okay, like that. So work energy theorem, this is one of the most important theorems. Okay, work energy theorem is very important because work energy theorem basically says that work, the net work, okay, this is important, net work, net work done on the system always is always equal to the change in kinetic energy. So there is a derivation regarding this. There are actually multiple derivations for just this formula. Based on a ninth standard student, the derivation in the textbook is different. For a 11th standard student, the derivation is different. For students who are pursuing other MSc courses, the MSc physics, the derivation there is different. Okay, but nonetheless, just remember that all that derivation just means this: net work done for a system is equal to the change in kinetic energy. And why is this so important? Because net work is equals to half m v final square minus half m v initial square. So the reason it is very important is that, let me tell you, there are certain equations in mechanics that are very important, and one of that equation is this work energy theorem, and the other one is energy conservation. That is just a simplified version of work energy theorem, and the other one is momentum conservation. These three are very important because these will help you calculate velocity when work or force is given. Okay, if in the question they asked you to calculate force or work, you can just calculate it based on the given things. But velocity, when you are calculating, you will need either this equation, work energy theorem equation, or momentum conservation, or energy conservation equation. Okay, so that is why my sir told me that work energy theorem is so important that when you are asked to calculate velocity, this equation is really important. Okay, so you can read all this. Well, network, by what do I mean by network? So let us look at it. So be it any kind of work, be it work done by spring force, be it work done by gravity or be it work done by any external force, uh, be it work done by friction, always leads to change in kinetic energy. Okay, so where is potential energy? Where is other forms of energy? Well, potential energy is basically, for example, if we take gravitational potential energy, it is the negative of work done by gravity. Okay, it is the negative of work done by any external force. Potential energy is basically the negative of work done by external force is equals to the, sorry, let me tell you, work done by external force is equals to the change in potential energy. Okay, work done by any conservative force is negative of change in potential energy. I hope you understand this. Right. So, for example, if we have a force, let's say a force, external force, it brought this block of mass m to a height h. So, the work done by external force is basically the change in potential energy, gravitational potential energy, that is mgh. This you all know. But if I ask you the work done by gravity, which is a conservative force, it will be the negative of this, because you see mg is acting downward and the displacement is upward, right? So that's why negative sign is important. So potential energy, gravitational potential energy, spring energy, external force, work done by friction, all these come under the net work done. Okay, and then they all equal to the changing kinetic energy of the system. So if the system is initially at rest and finally also at rest, then uh, the conservative forces equal to the external forces. Okay, uh, you can get it from this equation. So now let me just add one more page. Yeah, it's already added. Okay. So now let us talk about work done by normal force. So let's say a body is like this acting. So normal force is here acting normal, and then mg is here. So what is normal force? Normal force is a contact force between two surfaces, and it always acts perpendicular to the body. So if you might have learned it in Newton's laws of motion, that if you have a circular body like this, and let's say you have yeah, so for this body, normal force always acts perpendicular to both the surfaces. This is normal 1, this is normal 2, you see. So here also, here it is, for this block the normal force is acting upward, you see, perpendicular to the body. So once, if I make the displacement of this block upward, then this normal force, as soon as the block just leaves contact with the ground, the normal force becomes zero. That means there is no work by normal force. But gravitational force, it will keep on acting. It is an external force, it keeps on acting on that block. Okay, nonetheless, normal force is also an external force, but it is a contact force. You should understand this. Once the contact is once the block left the ground, the normal force becomes zero, and but gravity still acts on it. Okay, it is a, it acts on it. So now if I lift this block, let's say at a height h, okay, height h, just take off this, work done by normal force, as soon as it leaves the contact, normal force stops acting. So because of that, work done by normal force becomes zero. Work done by gravity, gravity will still act. Be the body may be anywhere, gravity always acts on it. Okay, until unless you're in outer space. But gravity, as it is acting, it will be mg h. Okay, force into displacement, right? So that is what I meant to say, that normal force always act perpendicular to the body, and work done by normal force is always zero, always zero. Okay, because once the body leaves the contact, normal force is zero and work done is zero. That's it. So now we'll be looking at different forms of energy. Okay, so now this is what is important. So kinetic energy, I'll be writing all the formulas here. Basically, kinetic energy, it is the energy uh, of a body due to the virtue of its motion. This is just a basic definition. Nonetheless, what is useful for you is the formula, that is half mv square, and then gravitational potential energy. Potential energy has different forms, so it is necessary to mention gravitational potential energy. But nonetheless, whenever we talk about potential energy, whenever we just say potential energy, it means gravitational potential energy only. So it is mgh. Okay, now spring potential energy, it is half kx square. I'll just do a small derivation here. If I have a block like this, okay, okay. So this is mass n, not needed, but the spring constant is k. Okay, so initially this was the natural length. This is the extension, initial extension. Now I brought this block here. So this is the final extension, all right? This is the final extension. So now, like I said, work done by any force is okay, it is this. So here we know that work done by spring is kx into dx xi xf. Okay, so here as this is expanding, the force of spring is backward, so that's why there is a negative sign that we put. Like I said in the example of work done by friction, we generally put a negative sign from our side. So this will come out to be half k x final square minus x initial square. Okay, with a negative sign here. This is the work done on a spring. Okay, work done by spring force. Yeah. Okay, any doubts still here, guys? Any doubts, you can just drop a message, or like you can unmute and speak. Okay, so now what is potential energy by spring? So let's say a body initially at natural length, and it is expanded to some extension. This is the natural length. Okay, initially at natural length, it is brought expanded to some x distance. So initial will be 0, right? Work done by spring force, if you see initial expansion is 0, then it will be negative of half k xf square. So now, like I said here, there, work done by conservative forces is negative of change in potential energy. Therefore, change in potential energy, sorry, this should be work actually, will be negative of this, that is half kx square. So this is the potential energy of the spring. Whenever we solve questions, we generally see that energy conservation, that initial energy of the spring is at natural length, and final energy is half kx square because it has expanded by an x distance. Okay, so this is the potential energy stored in a spring, be it expansion, be it compression. This is what it is. Okay, if this x can be expansion or compression depending on the situation. Okay, we'll solve some problems in another session. Right now I'm just brushing up all the concepts. So this is done, potentiality is done, spring force is done, and then what else is left? Potential energy, kinetic energy, and then let me just check. Elastic energy. Okay, so that's it. So this whatever you see, now let me just this is a advanced level concept. uh, if you don't understand it's okay, but I'll just teach it. If I have a body at a radius r from a fixed surface and it is rotating with a velocity, let's say v. Okay, so it is actually going in a circular motion. Yeah. So this body has a rotational energy and a kinetic energy. That is, kinetic energy is square. Rotational energy, if you look at it, force acting, central force is m b square by r, right? M b square by r. You can write this as m omega square r. Omega is in circular motion. I'll teach you what omega is. I'll teach you vertical circular motion there and horizontal circular motion also in a separate chapter for circular motion. Okay. Omega is, this is not work actually. This is omega. Let me start copying. Omega is velocity by r. I'll tell you what omega is in upcoming chapter. Okay. If you look at this, this looks similar to kx, right? This is the x distance, if you see. So if the radius of this orbit is increasing like this in a spiral version, then you can just write work done by this force. Oh, sorry. Work done by this force is equals to half k m omega square x square, that is r square, right? So this is work done by any force for a body that is changing its radius. Okay, till now even JEE advanced didn't ask a question regarding this topic, but I just thought it just came in my mind, so I thought of teaching it. If you didn't understand, I'll explain it again with a good example in the next class. Okay, so now we are coming to one of the most important topics, that is equilibrium. Okay, so equilibrium, if you see, let me just tell you, there are three types of equilibrium. That is, one is stable equilibrium. For example, you have a body like this. This is the best example for a stable equilibrium body. You have a block like this. Okay, so this is what we call as unstable equilibrium, because once, just if the body slightly moves, or just if you give a small jerk, or like if you give a small impulse, once this body displaces here, it will just directly fall. Okay, uh, if you give it an impulse forward, this body will fall down. If you give it an impulse backward, this body will fall down, right? So this is unstable equilibrium. If you have a body, let's say here inside, now if I give a small impulse to this body will travel here and then again come back to its original position. If I give an impulse backward, it will go up and then come down again. So this is stable equilibrium. This is stable equilibrium. So basically, equilibrium, be it stable or unstable, the thing is, for a stable equilibrium, wherever the initial position of the body is, Once you move it from that initial position, it will come back to its initial position. Okay, and if you be it any direction, okay, be it forward or backward direction. Okay, so now for unstable equilibrium, where a body is kept in such a manner that once you give a small change in its displacement, that body won't return to its initial state. So it will either go to a different final state, or with a forward push or a backward push also, it will go to a different final state, but it won't come to its initial state. So that is unstable equilibrium. So there is another equilibrium that is not that important though, but it is still questions come. Neutral equilibrium. Okay, so basically, if I give a push to this body, okay, I'll just teach you with an example. Okay, these examples they don't usually ask, but let me tell you. So generally, what questions come? How do the questions come? So they'll give you an equation of let's say any equation like this. Okay, for potential energy. Okay, this is the gravitational potential energy in the form of any equation of, let's say, f of x. Okay, f of x. They give you any equation like this, and you're asked to find out whether the body is in stable equilibrium or unstable equilibrium. So for that, let me tell you, force is the negative of change in potential energy, external force. With this, you remember this formula. You remember, okay? Force is the negative of change in potential energy with respect to the function, the dependent function. So, depending on what the force is, we can calculate the stable or unstable equilibrium. So, if I say that a body is in equilibrium, that means that du by dx is basically just zero. Okay, for any kind of equilibrium. So for stable or unstable equilibrium, there is a chart that is given here. You have to double differentiate. Okay, d square u by dx square. This you will calculate, and then if it is greater than zero, it is stable equilibrium. If it is negative, then it is unstable equilibrium. If it is zero, just zero, then neutral equilibrium. I'll tell you with an example. So let's say that you have a graph like this. Okay. So if a body is here, this is a graph of potential energy versus x. Okay, so when you are calculating the slope for this graph, the slope of this graph represents the force, right? The force. So now for the body kept here at a point A, let's say, and point B, let's say point C. So if you just let's say you're calculating the slope of this body here. If you calculate the slope, this force here comes as negative. The force is negative for this body, right? The body at position A, if you just look at its left side, and you calculate the slope, it is coming as negative. It is, the slope is positive, but the force is negative because F is negative of du by dx, right? So it is negative. That means it will travel in this direction, negative x direction. That means it is not coming back to its original position, that is at position A. This means this is unstable. If you look at the right side of this uh, position A, you'll see that the slope is negative, but the force is positive because slope is negative of du by dx. I have written it here, right? So that means that it will go to a positive direction because force is positive. The x displacement will also be positive. That means it won't come back to its original position, that is A. So this is unstable equilibrium. I'll just write it neatly. Unstable point is A. If you look at, if a body kept at position B, if you look at the slope here, this is coming as positive. If I just displace this point B, position of this block B from point B to here, you'll see that the force acting is negative because this you see du by dx is positive, right? But force is negative of du by dx. That means force is acting in the negative direction. That means this block, if I push it this side, Because of that force, because of the force acting, it will come back to this side. That means it is stable equilibrium. From this example, stable equilibrium. What is stable equilibrium? Once the object is pushed, it will come back to its initial position. That is stable equilibrium. So this is what it is happening here. Neutral equilibrium is basically, here the slope is zero. That means force is also zero. Then it is just in equilibrium. Be it neutral, call it neutral equilibrium or just normal equilibrium. It is nothing is happening. If you push it, it won't come, and if you push it in the backward direction also, it won't come back to its initial position. That's it. Okay, so this is a formula sheet of all the reviews that I have given just now. You can see that elastic potential energy, it is half kx square. Conservative forces, this is what you do. Variable forces of short range, yeah, f dot. This is the formula that I gave. And work energy principle. This is work done by spring force. Like I said, initial, final. Energy conservation. Yeah, energy conservation. I'll talk about it right now. Increase in potential is decrease in potential. I'll talk about it. This is it. Variable force. Force and half k square. Okay. So I have to talk about what energy conservation and okay, energy conservation. So there are different ways of energy conservation. If I say that, coming back to work energy theorem, energy right. So for any body, there is no action. Energy conservation. I hope you understood this line. Let me tell you. So work energy theorem, we wrote it as W net work done on the body is equal to the change in kinetic energy, right? So this net work done, it is made up of two forces, for two work done. So basically, work done is just classified into two types. One is conservative work, and then non-conservative work. That's it. And then kinetic energy and potential energy, these are different kinds of energy. That's why it is work energy power. Energy is a bit different from work, even though the units are same, but the definition is different. Okay, so work done by conservative force plus work done by non-conservative force is equals to change in kinetic energy. This is work energy theorem. So if all the non-conservative forces acting on the system is zero, then we get all the work done by conservative forces is equal to the change in kinetic energy, right? So like I said, work done by any conservative force is equal to negative of change in potential energy. So negative of change in potential energy is equal to change in kinetic energy. So this is what is the first step towards energy conservation. So you can't randomly use energy conservation, even though it is one of the most important equations. You have to know when it can be used. Whenever there is no non-conservative force acting on a system, then only you can use energy conservation equation. So only if and only if conservative forces are acting, then only you can use energy conservation. So this equation has its own significance. That is, for a system, for any system, the decrease in potential energy is equal to the increase in kinetic energy. Okay, let me be a bit specific here. For example, let's say there is a hill. Okay, Here's a hill. Okay, so here you see there is a car here. Okay, this car is traveling with v velocity, and its initial velocity became zero. Sorry, its final velocity became zero at the top. It is at a height h. Okay, so here what is the initial potential energy? So let me tell you, potential energy is it is not absolute. What do I mean by absolute is that you can't define the potential energy of any body. You can only define the change of potential energy. So whenever I say the potential energy of a block at a height h is mgh, that does not mean that the potential energy of that block is actually mgh. It is a change in potential energy. So initially, when it is at the ground, I assume the potential energy to be zero. I assumed this is not absolute. I assumed, I took this as reference, I took ground as reference. Reference is always zero. This is called datum level. Actually, you learn it in higher standards, higher studies, that this is called datum level. So any object put at datum level is the potential energy becomes zero. So whenever I say that the potential energy of a block is mgh at a height h, that means that the final energy minus initial energy, final energy is mgh minus initial is zero. That means the energy, potential energy of this block is mgh at a height h, because initial energy is zero. That is, I took ground as a reference. So basically here also, initial energy, initial potential energy is zero, but it does have a kinetic energy initially, that is half mv square. And at a height h, the kinetic energy becomes zero, but the potential energy has increased, that is mgh. And again, when this will come down, uh, let's say it comes down with a velocity u again, with a velocity v. Okay, final kinetic energy is half mv square again, right? So basically, initial potential energy was zero, but the kinetic energy was half mv square. But as the potential energy increased, the kinetic energy decreased. You understand that the kinetic energy decreased. Let me give another example. Let's say a block is kept here, or let's say this is some object. Okay, so initial potential energy is mgh, kinetic energy is zero. Once it came here, potential energy became zero. Now it has some kinetic energy, half mv square. And in fact, we can calculate this velocity also. As there is no other non-conservative force acting, we can just directly write from energy equation that potential energy is equal to the kinetic energy, gh, implies final velocity is 2 root gh. This is what we also learned it in kinematics, right? Okay, so now we have actually reached the end of the chapter. I'll just write one more equation here. So energy conservation is initial potential energy plus initial kinetic energy is equals to final kinetic potential energy plus final kinetic energy. Okay, so this is what is the energy equation. Okay, this is energy equation. So there are actual different applications of energy equation. I'll take another session, maybe tomorrow, or on Friday. I'll notify it in the group. So based on that, I'll take around 10 questions, good level questions, that we'll solve in the class. Okay, so this is all the brush up of work energy power, and I think there are only few people left in the class. So if so yeah, any doubts, anyone? Okay, Madhu is only left. Madhu, is there any doubt about the session so far? Okay, I think there are no doubts. Hari? Yeah, we'll wrap it up. Okay, so this is the end of the revision.